Hey everyone, and welcome. Today we're going to get into a force that's hiding in plain sight inside every single one of your electronic devices. We're talking about electrical resistance. You know, the unsung hero that's secretly controlling, directing, and even creating energy in the world of circuits. So let's get right to it. So to kick things off, let me ask you something. What do you think a kettle boiling water, a garden light that flicks on by itself at night, and your phone screen that magically adjusts its brightness all have in common? I mean, they seem totally different, don't they? But believe it or not, they are all connected by one single fundamental principle of electricity. And that's the answer. They all have to master electrical resistance. See, it's not just some obstacle to overcome, it's actually this incredibly powerful tool that engineers use to make tech work for us in some really clever ways. Okay, so here's the plan for the next few minutes. We're going to define what resistance is and take a look at Ohm's law. Then we'll see who follows the rules versus who breaks them. We'll find out what actually controls resistance, how we can turn it into useful things like heat, and meet some smart resistors. And then we'll wrap it all up by putting the theory into practice. All right, let's start at square one. What in the world is this thing we call electrical resistance? You can basically think of it as electrical friction. So as electrons are trying to zip through a material, they're constantly bumping into and colliding with the atoms inside it. That opposition, that difficulty of flow, that's resistance. We measure it in ohms, and we find it just by dividing the voltage across something by the current going through it. And this whole relationship is captured perfectly by a little something called Ohm's law. For a whole bunch of materials, especially metals that aren't getting hot, it's super simple. Double the voltage, you double the current. It's this clean, direct relationship where R equals V over I that is really the foundation for pretty much all circuit analysis. But, and this is a big but, not everything in the world of electronics plays by these rules. And that brings us to a really important split. The components that follow the rules and, well, the ones that break them. The way we tell them apart is by plotting what's called an IV graph. It's just a chart showing current versus voltage, and it's basically like a unique signature for every component. Now, for something that does obey Ohm's law, we call that an ohmic conductor. Its signature is a perfect straight line that goes right through the 0 point. That tells us its resistance never changes. So here's the bottom line. Ohmic conductors, like your basic everyday fixed resistor, have a constant resistance and a straight IV graph. Easy. But the non-ohmic ones, they're the rebels. Their resistance actually changes depending on the voltage or current, which gives them a funky curved IV graph. The filament in an old-school light bulb or a modern diode are perfect examples. And you can really see just how different these behaviors are right here. The ohmic resistor, nice and steady. The filament lamp, whoa, its resistance shoots up as it gets hotter. And the diode, its resistance changes so drastically depending on which way the current's going that it's a true electrical gatekeeper. Yeah, a diode is pretty much a one-way street for electricity. If you push current through it in the forward direction, its resistance just drops to almost nothing, and current flows right through. But try to send it the other way, what we call reverse bias, and its resistance becomes practically infinite. It completely blocks the flow. This little trick is what makes everything from charging your phone to building computers possible. Okay, so if resistance isn't always a fixed thing, what actually controls it? Well, it turns out there are 4 main physical properties that decide how much resistance any given object has. First up, length. It's pretty intuitive. The longer a wire is, the more stuff electrons have to push through, so more resistance. Second is area. A thicker wire is like a wider highway, more lanes for the electrons to travel in, so it's an easier journey, which means less resistance. Third, temperature. For metals, when things get hot, the atoms vibrate like crazy, getting in the way of the electrons and bumping up the resistance. And last but not least, the material itself. I mean, some materials are just born to be more resistive than others. And I love this analogy for area. Imagine an electron is a waiter trying to hustle through a packed restaurant. A narrow room or a thin wire is going to make it really tough to get through. But a wide open room, a thick wire, gives that waiter tons of paths to take. It's just easier. Less hassle means less resistance. So that fourth factor, the material, is measured by a property we call resistivity. We use the Greek letter rho for it. Now, resistivity is an intrinsic property, kind of like density. Copper will always have the same low resistivity, no matter how you shape it. It lets us figure out the resistance of any object as long as we know its dimensions. So far, we've kind of been talking about resistance like it's a problem, an opposition. But it's not always the bad guy.
In fact, we intentionally use it to do some incredibly useful things, like making heat. So electrical power is just the speed at which energy gets used. The basic formula is super simple. Power is just voltage times current. But by plugging in Ohm's law, we can rewrite that in terms of resistance. And that gives us two more really handy formulas. Power equals current squared times resistance, and power equals voltage squared divided by resistance.
And this brings us full circle, right back to our kettle. The heating element inside is designed to have a really high resistance. When a ton of current gets forced through it, all those collisions between electrons and atoms turn electrical energy into heat. We call this joule heating, and it's exactly how your kettle, your toaster, or your space heater works. See? Resistance isn't a bug, it's a feature.
Okay, but what if resistance could change on purpose? Some components are designed so their resistance changes in very predictable ways based on what's happening around them. These are what I like to call smart resistors. Let me introduce you to the two stars of this show. Over on the left, we've got the light-dependent resistor, or LDR. Its resistance changes based on how much light is hitting it. And on the right, we have the thermistor, whose resistance is all about temperature. Let's see how they tick. This table lays it out perfectly. For an LDR, the brighter the light, the lower its resistance gets. That's the secret behind how your garden lights know to turn on when it gets dark. And for the most common type of thermistor, an NTC1, as the temperature goes up, its resistance goes down. That's the key part in everything from your home thermostat to the fan controller keeping your computer from overheating.
All right, that's a lot of theory. It's time to see how this stuff is actually used to solve real problems.
Let's just walk through this one. The goal is to figure out the length of a copper wire. We're given its diameter, its total resistance, and the known resistivity for copper. So, step 1, we calculate the cross-sectional area using the diameter. Step 2, we take our resistivity formula and just rearrange it to solve for length. And finally, we plug in our numbers, do the math, and we find out our wire has to be 18.4 meters long. It's a perfect example of how it all connects.
And that leads us to a final question to chew on. We've seen how we control and use resistance, so what's next? What happens if we could engineer materials with practically zero resistance, superconductors, or materials where we could tune the resistance perfectly? What kind of new tech could we unlock? Think about power grids with no energy loss, or revolutionary new kinds of computers. That's where understanding resistance really takes us. Thanks so much for joining me.